In the previous two segments, we learned how the deformation gradient maps curves and surfaces, and in particular, we learned this through the mapping of tangents. We'll proceed with this idea and move on now to volumes. Okay, so the question we are asking now is how do volumes get mapped? All right, and this idea again can be expressed or can be elucidated with our props. We have our body in the reference configuration. Now imagine, you'll have to imagine this because I can't quite show it to you. Imagine a volume on the inside of this body. Okay, we're asking now the question of how that volume changes under the deformation. So imagine a little volume inside here, an infinitesimal volume, okay? And now as the body deforms, we're asking how does the squeezing of the material or the stretching of the material change that little infinitesimal volume, okay? All right, the way this happens is the following. As always, we have our basis, we have the body in the reference configuration, and I'm going to draw a little elemental volume here. Okay, let's assume that the vectors that define the sides of this little volume, right? These vectors are denoted, I've drawn them nominally I've drawn them in fact along the basis vectors. So let's just call these vectors, if I call the basis vectors E1, E2, E3, let's just call these vectors, this one would be EC2. That vector would be C1 and that vector would be C3, right? Okay. Imagine that these are all infinitesimally small vectors, okay? Of course, this volume does not need to be anything like a cube or even a or even like a rectangular prism or anything like that, right? We just need that those are three vectors and the angles between them are arbitrary. Okay, so what we're asking now is under the deformation phi, what happens to that little volume, right? And let's draw it considerably deformed here. Okay. This vector now is what came from here. The other two vectors that we have in this picture are that one and that one, right? So this vector we know because after all it's a tangent vector, right, to the material. So we know that this vector is FC1, FC2, right? That vector is FC1 and that vector is FC3. Okay, simply by the fact that those are after all three tangent vectors scribed inside the body, right? Okay, now we know that in this configuration, if we denote that volume as D capital V, that infinitesimal volume as D capital V, right? and this infinitesimal volume as d little v, we have the following relation, right? So infinitesimal volumes d capital V equals C1 cross C2 dotted with C3. Okay? D little v equals F C1 cross F C2 dotted with F C3, right? Just from our notion of the scalar triple product, right? And now, of course, a result that we actually already used in our proof of Nansen's formula tells us that dV is simply determinant of F d capital V. Okay? This is how the deformation gradient maps volumes. Now, an important requirement for our description of continuum mechanics is that the ratio between these volumes has to stay positive, right? So, the condition is what is called the local impenetrability of matter. Okay? It says that the determinant of F has to be greater than 0. This should be pretty obvious, right? Because if the determinant of F is equal to 0, we're saying that we start out with some non-zero volume element in the reference configuration, but under the deformation, we've squeezed that material to nothingness, right? That obviously doesn't work. Okay, so that violates a basic principle that we will adopt all along. Along those same lines, can you think of what it would mean for the determinant of F to be negative? Of course, you may think of a continuous process and say that, well, if the determinant of F starts out positive and goes negative, it has to pass through 0, which means material has to disappear and then somehow reappear, right? Or we're talking of taking this volume element, taking a little volume element inside here, squeezing it down to nothing, and then having it show up again. But mathematically, or actually even geometrically, what does it mean for the determinant of F to be negative? Think about it for a second. We can answer that question by using this triad. Okay? We've been using this triad all along for our basis vectors, but now just for now, imagine that they're no longer basis vectors, but in fact refer to the three vectors by which we defined our volume element in the reference configuration. Let's suppose that the vectors are C1, C2, and C3. Defined as such, they form a right-handed triad, right? And we know that if we calculate C1 cross C2 dotted with C3, we get a positive number because they are right-handed. Yes? If we turn this around and do that, C1, okay, now this is under the deformation. This is FC1, that is FC2, that is FC3. If we form the scalar triple product of these three vectors, we will get a negative number, right? And essentially that's what having a negative determinant of F means, right? It means that one of the vectors, right, has been essentially, you've deformed it to such an extent that this vector somehow is actually flipped through. You've made the material, and the way to do that would be, of course, you can now imagine making this vector smaller and smaller under the deformation, right? There you go, it made it smaller, make it even smaller. Okay, my Lego pieces end there. Okay, so make it smaller, right? Made it even smaller, passes through itself, it's gone to 0. At this point, the determinant of F is equal to 0. and now you reconstruct the vector here, right? That's what it means. It means that one of the vectors has been sort of shrunk down to 0. You've turned the volume into a surface. Determinant of f equals 0. Showed up on this side. Determinant of f is now less than 0. Okay, that too is disallowed. Okay. All right. Let's just observe a couple of more properties of the deformation gradient. Let's see what the deformation gradient does to the angle between two vectors, right? The angle between two vectors. Okay, so in this configuration, in the reference configuration, we have two vectors, say u and v. Okay, and now the deformation takes them to fu and fv, right? Okay, so we know that we can describe the cosine of the angle between u and v as follows, right? The cosine of the angle between u and v in this configuration, I'm going to denote with a capital theta. Okay, we know that cosine of capital theta is u dotted with v divided by the magnitude of u dotted with v. In this configuration, in the deformed configuration, let's denote that angle with a lowercase theta. Okay, so cosine theta is fu dotted with fv divided by the magnitude of fu dotted with, sorry, I realize that I made some mistakes here in the numerators of both sides, so let me fix that right away here. On the left hand side, I need the magnitude of u and the magnitude of v. That gives us the cosine. And here I have the magnitude of fu and the magnitude of fv. Okay? Clearly, these are not going to be the same, right? In general, cosine little theta is not equal to cosine capital theta. Okay? And really all this is saying is that the angle between vectors is changed, right? So if this is the angle between two vectors in the reference configuration, they deform, the angle between them in general changes because of the deformation. Okay, and that's expressed by the fact that cosine little theta in general is not equal to cosine capital theta. Okay, to finish off this segment, I want to spend just a few minutes talking about a slightly more mathematical way to think about the effect of f upon the deformation. Okay, and this is this little subtopic is going to be titled the role of the deformation gradient in the relation between positions of points. Sorry, that's a bit of a mouthful for the title of a subtopic, but that's just the way it is. Okay, right. So now here's what we're talking about. Again, reference configuration. We want to look at 2 points. Let's suppose we have a point capital X and another point capital Y. Okay. Under the deformation, these points go to little x and little y. Okay, so we're going to ask ourselves the question, how the distance between points little y and little x is related to the original distance between them, capital Y and capital X. Okay, and now as we start going along with this topic, I won't write down every little thing in great detail. Okay, so here's how we want to think about it. Okay, consider the following, right? Consider y, which we could write now as x plus y minus x. Okay? Now, we know that little y equals phi of capital Y comma t, and little x is phi of capital X comma t. Okay, so then we know that y minus x, which is the vector going from x to y and really tells us about the distance between x and y and also gives us the direction, right? We know that this is now from the previous line. We can write this as phi of y. Let me put the t here, okay? Because time doesn't really play a big role in what we're trying to do here. Okay, so it's phi t of y minus phi t of x. All right. Now, I'm going to write phi t of y using a Taylor series expansion, right? So again, we have y minus x equals phi sub t of y, but remember we decided on the previous slide that we could write y as x plus y minus x, right? Minus phi t of x. Okay. Now, what I'm going to do with the first term on the right hand side is expand it in a Taylor series. Okay, and I'm going to expand it in a Taylor series about capital X. Okay, the way this is done is to write it as phi t at x plus the partial of phi t with respect to x, okay, evaluated at the point x, right, acting on y minus x, okay, plus we get other terms which are of order y minus x square, right, higher order terms. All of this minus phi t of x. Okay? All right? Now, those terms cancel out, right? So it tells us, therefore, that the distance between points x and y, in fact, the vector separating them under the deformed state, is is essentially f sub t evaluated at x, right? Because that is exactly what we have here. From the definition of the deformation gradient, okay, plus higher order terms. Okay, so what we see is that if the original distance between y and x is small, right, then the deformation gradient, oh, I need to have a y minus x here, sorry. I need to have a y minus x here. Okay, now we see that if the original distance between points x and y is small, right, then the deformation gradient is a first order approximation, right, to the distance between x and y, or to the vector separating x and y in the deformed configuration. Okay? So it's in this sense that f is also defined as is also referred to as a first order approximation to the vector separating neighboring points under the deformation. Okay? It's essentially a first order approximation to the total deformation. And if the points y and x are sufficiently close, those sorts of terms can be neglected. All right? This sort of an idea will be the basis as we come back after this segment and start talking about strain.